So the electric potential is governed by this equation, and the charge density, which we can write as rho e, which is basically minus epsilon e d2 phi dy2, that becomes minus epsilon e. Now if I differentiate this equation, so 2 times k square zeta cos hyperbolic again ky by cos hyperbolic kh. Now the electric potential equation, phi electric potential is phi minus E0x. Already we have written over there. So you get phi minus E0x. Now because so what we have is del phi del x. Del phi del x becomes minus E0x because this phi is, small phi is independent of independent of x. So the momentum equation becomes mu d2u dy2 equal to minus E0 rho e equal to minus E0 epsilon. Already we have obtained the so minus plus. So E0 epsilon e kappa square zeta into cos hyperbolic kappa y by cos hyperbolic kappa h. So this is the momentum equation. Now it is reduced. So with the conditions on y equal to 0, you have y equal to u equal to 0, and symmetry condition y equal to, okay, we are putting this way, y equal to h on the lower wall, y equal to h, we have u equal to 0, and y equal to 0, du equal to dy 0, symmetry condition. So this is on the wall. So if I now integrate with these two conditions, so what I get is, if I now first integrate du dy, so du dy equal to epsilon e E0 kappa square zeta by mu, and 1 kappa get cancelled. So what we have is sin hyperbolic ky by cos hyperbolic kappa h plus b becomes 0 because of the second condition. So now again if I integrate further, so what I get is epsilon e E0 zeta by mu into cos hyperbolic kappa y by cos hyperbolic kh plus a. Now what we have is u equal to 0 and y equal to h. So this gives the situation. So a becomes minus epsilon e E0 zeta by mu, because cos hyperbolic is h, both get cancelled. So what we get now, u equal to, if I take this common, so by mu 1 minus cos hyperbolic ky by cos hyperbolic kappa h, not ky. So this is the electroosmotic velocity. So this is the EOF velocity profile. Now if we define this UHS, basically this is referred as the Helmholtz-Malczewski equation by this manner, a parameter by this way. So U becomes UHS into 1 minus cos hyperbolic ky by cos hyperbolic kappa h. Now, if I consider the average flow or volume flow rate, so that means the volumetric volume flow rate per unit width in the of the slit microchannel can be governed by Q equal to 0 to H. So we multiply by a 2 because symmetry we have assumed. So Uy dy. So this Q becomes 2H UHS into 1 minus tan hyperbolic kappa h by kappa h. One can very easily deduce this formula. So average flow means if I divide by Q by 2H, that is the average flow, and to just to say once more, this is the velocity profile is, no, here it is UHS. So UHS into 1 minus cos hyperbolic kappa y by cos hyperbolic kh. Now, a few important things from here. Say kappa h, which is nothing but the h by lambda, that is the ratio between the channel half height and the device length. So normally it is small. Now, if lambda is very small, that means thin EDL. So we have kappa h is very large. Then kappa h is very large. In that case, what we find that the Q, then so the Q is becoming QHS for thin device length. For a thin device length, what we find that Q equal to 2H UHS. So that means average flow is the average flow for thin device layer for a thin device layer is UHS. And also the velocity profile, it shows that if U approaches UHS very quickly if kappa is very large as we increase the h. So another thing is that this Q, what we obtain from here, so this is independent of device length, and also this UHS, which is independent of h. This is a independent of the channel height. This is a very important characteristics, because we will be considering only the very low channel height, no low channel dimension. So what do you find that if it is a thin Debye length, so we get a UHS which is becoming independent of H. Okay. Another thing is that from here, the this term from this, what do you find that when kappa H is of order 1. So that means if not for finite value of lambda, the Debye length, that means it is not very thin. So what do you find that Ui, then Ui or for that matter the average UHS is reduces as kh increasing. So now I will show some profile for the velocities in this slide. Now this is the modal fraction basically. So what we defined before, that was the CI C1 C2. So if I divide by C0, so that is basically the same F and G. Now see this velocity profile. What we are finding that this is the lambda is the Debye layer thickness. So lambda is nanometer. See, if it is nanometer is 0.8, we are becoming a flat profile. So that means the flow within the core is flat, and if lambda is low, I mean lambda is high, so say 8 nanometer, lambda is high, that means the kappa is low. So what do you find? A kind of parabolic profile is occurring. Okay. So this parabolic profile is situation is occurring. And also if you see the distribution of ions, so this is also some important information this plots convey, is that if the Debye length is very thin, say this is 0.8 and this is the distribution of cation and anion, they are same. So that means if I now sum up the charge density which is proportional to G minus F, F capital F, the Faraday constant into G minus F. So what you can find that G minus F is 0 on the core. So within the core, the fluid can be treated as electrically neutral if you have a situation where Debye length is very small. Okay. So 0.8 nanometer, even if you go further, so we will have the situation, it will be a situation like a flat profile, and it is also referred as a plug-like profile and a electroneutral velocity. And however, when you have the condition, when you have the Debye length is some order 1, that means Debye length is comparable with the channel height. So you get the situation a parabolic flow profile. Now, yeah. So this the way of modeling the electroosmotic flow is referred as a Poisson-Boltzmann model, because here the ion distribution are governed by the Boltzmann distribution, and the electric potential is obtained by the Poisson-Boltzmann equation. So here we have assumed a equilibrium situations. So we can now describe the shortcomings of the Poisson-Boltzmann model, because obviously the Poisson-Boltzmann model is not the self-sufficient, but that will not be the taking care of all electrokinetics of any kind of situations. Now, what are the limitations of the Poisson-Boltzmann model? First of all, here we have taken a ZZ electrolyte. Now, And also another thing is that we have considered here the Debye-Huckel approximation. Of course, one can generalize even beyond this jet-jet electrolyte situation. That means instead of binary electrolyte, you can have several multivalent situations. So that can be generalized. So, but the Debye-Huckel solution, what we just discussed for the electroosmotic flow, have the limitations. Now, flux of ions normal to the charged surface is assumed to be 0, which is only true if you have the Debye length is very small. Convective transpose of ions is neglected, which is also may not be valid in several situations. Now, for a thin EDL or electric double layer, the EOF velocity, what we found is approaches to the UHS and becomes 0 within the core of the channel. This implies that an electroneutrality outside the thin EDL develops and velocity rapidly approaches from 0 to the wall value, 0 on the wall value to the UHS outside the EDL. For finite value of the Debye length kappa h, the average EOF velocity becomes lower than UHS and it becomes smaller with the reduction of kh. Okay. And volume flow rate enhances. This is quite clear from the expression we have derived, whatever we have derived in the previous slides. The volume flow rate enhances with the rise of the kh and attains saturation for thin EDL when kappa h is large, very times greater than 1. Here this should be a kappa, so I will better write over here. This is an important observation, that is the volume flow rate of EOF rises with the increase of kappa h. In other words, reduction of EDL kappa h, and it attains a saturation UHS for kappa h many times greater than 1. For large kappa h, it approaches saturation, what we have shown also graphically. Another thing is that the electroneutrality, or if you see the charge density equation rho e, so this rho e becomes 0 when you have the, so when kappa h is very small, so kappa h is very large, so what you find that this becomes 0. So that means a electroneutrality condition appears for a thin outside the thin Debye layer. So in this process, a velocity slip model can be prescribed like this way. That means one can assume that the Debye layer, a situation which is appearing very close to the double layer, close to the charged wall, and within the Debye layer you have a rapid change in the velocity and the electric potential, and outside that Debye layer you have the constant electroosmotic velocity, which is governed by that UHS, which is basically the Helmholtz-Smolchowski equation, and a electroneutrality established. Now the Debye layer are very thin. Debye length will be of few nanometer, even lower than nanometer. So kappa h, if I take the h is the channel dimension, so kappa h is normally quite large. So that means outside the Debye layer we can consider a slip model can be prescribed in this manner. So that means we can treat the flow from the edge of the Debye layer, and we impose a slip velocity condition governed by the Smolchowski velocity UHS. Velocity at the edge of the double layer is governed by the Smolchowski velocity E0 epsilon E zeta by mu. Now, the sign is inside the zeta, so if it is negatively charged, so we can take minus zeta and plus zeta, whatever. And the free slip condition on the outer edge of the double layer is based on the assumption that the electric field lines are tangential to the outer edge of the diffuse layer and no transport of ions across ions occur into or out of the diffuse layer. That is a very important thing to, I mean, as a big generalization or restriction for several cases. So, if you have a flat surface over, if we consider this interface as a very flat, so then we can impose this condition, and also if the external mechanism, that is the electric field, is weak, then only these conditions are valid. Another thing is that this boundary condition provides a linear relationship between the slip velocity and the local applied electric field. So, that is the main reason why the electroosmotic flow is considered to be a very sophisticated way of transporting fluid through channel, micro channels, because you see the average velocity is just a linear function of E0. So, now external electric field, which is can be controllable, which can be tunable. So, if I tune the electric field, imposed electric field, so accordingly I can have a larger volume charge density or low volume charge density. I can transport from one side to the other side. So, depending on the electric field I am considering. So, that is why the electroosmotic transport of liquid from one reservoir to the other reservoir in connecting by thin channels are much useful compared to the pressure driven partially flow. Now, if we look into the limitations, now here you see we have considered the binary electrolyte. So, and we define the ionic concentration is given by this way. Now, if it is a NaCl solution, say if the ionic strength is 0.1 mole of NaCl solution, so we can say the ionic strength of the solution is 0.1 m, which is half C0. So, basically that is what we considered a monovalent Z-Z situation. Now, a monovalent binary symmetric electrolyte. Now, if we have a situation like a salt Na2SO4 kind of situation, salt, so in that case the I is not the exactly the C0 by 2. So, one has to obtain the concentration of Na plus, which is just twice of the concentration of Na2SO4, and we get for a 0.01 mole Na2SO4, the ionic concentration is 0.03 mole. Now, in several situations, we may have the salt as MgSO4, K4, FeCN6 and this kind of things. So, here these salts are asymmetric 4:1 electrolyte, which are used to study electrokinetic theories. So, this creates a bottleneck for the Boyson-Boltzmann model, which we just described. Now, before looking into the other aspects or improve this model, so another comparisons we can make with the pressure driven flow. See, when we consider a flow through a channel which is under a constant pressure gradient. So, this is the pressure driven partially flow. So, what we have is that we impose a constant pressure gradient dP dx, which is say G, which is constant. So, the momentum equation is governed by this equation. So, mu del 2 u dy 2 equal to dp dx, which is equal to a constant. Now, on the channel wall, if we assume a symmetry again, u equal to 0 and on the surface, and u dy equal to 0 on the symmetry line. So, we get uy is given by this situation. So, ui becomes a parabolic profile. So, if we, this is the viscosity and the velocity profile, which shows a parabolic form. So, that means, if you have a pressure gradient flow, so the fluid velocity assumes a parabolic profile like this way. So, this is the x coordinate and this is the y coordinate. Now, if when we consider the electroosmotic flow, so that is a situation where we have a plug like profile. Plug like profile means you have, particularly in the thin Debye length, you have a situation that you have a within the core you have a constant velocity, which is UHS, and near the wall within the double layer you have a rapid change in this U. So, bulk of the flow is governed by the viscous diffusion, where the charge density is 0. So, you have a linear profile, which is absent in the pressure driven Poisson flow. In some cases, we like to have a plug like profile situation. Now, another very important important characteristic is that the volume flow rate per unit width for the Poisson flow is given by this way. That means, if I integrate uy, so which is nothing but 2h 0 to h u dy. So, if I integrate that, we get a situation like this way, h cube. So, that means it scales by h to the power 4. So, if I not know, because there is a g, in the g there is a x is involved, g equal to dp dx. So, if I consider a pressure drop, so dp dx can be taken as, if I have a pressure drop as delta p and the length of the channel is L. So, L equal to some few times h, which is in the order of dimension as scale as h. So, we can say that the volume flow rate is scales by h to the power 4. Whereas, if you see the volume flow rate for the EOF, what we just now we obtained, so this volume flow rate is just proportional of h. So, see, this is the volume flow rate for the electroosmotic flow, and for thin Debye layer, this is nothing but 2h UHS. So, this is for the thin Debye length situation, 2h UHS, whereas for the pressure driven flow you have a situation as given by this way and scales by s to the power 4. So, when you have a h which is many times lower than 1, so h is some 10 to the power minus of the order of 10 to the power minus 9 nanometer. So, some order of 10 to the power minus 9 nanometer. So, that means what you find is to have a fixed volume flow rate, you have to apply the g has to be enormous, which is impossible in several practical situations, particularly in drug delivery and other, where a very controlled amount of fluid to be injected through thin channel to the patient body. So, in that case, why if it is a pressure driven, that is, if you have a syringe and all, so what I find is that the pumping should be or the pressure drop should be enormously large, which is impossible, but whereas in the electroosmotic flow we can have a very sophisticated way to regulate the flow through this thin channel. So, next we will continue to the next lecture on the based on the Nernst-Planck model and so on. Thank you.